For the final part of this lecture, I'd like to discuss the concept of continuity, and specifically how to define a continuous functional, which is going to be a very important idea to develop before we develop the idea of the first variation or first derivative of a functional. There are, in fact, several different ways of defining what a continuous function is. Some of which are more advanced than others. The topological definition or open set definition of continuity is definitely one of the more advanced ways of defining continuity of a functional. However, it's not necessarily needed in one's first exposure to calculus of variations. So in this course, we're going to be sticking to what's known as the epsilon delta argument, otherwise known as the metric space definition of continuity. And this is because we have defined a norm on our space, and with that norm we have the concept of distance between elements in our vector space. So this can be easily generalized from single variable calculus into this infinite dimensional function space, which is what we're after. We want to generalize the results from single variable and multivariable calculus to infinite dimensional functionals. So we're going to start by recalling the definition of continuity in finite dimensional spaces, and then see how that idea gradually and very straightforwardly, in a very straightforward manner, develops into the idea for continuity of a functional. So recall that for a function of one real variable into one real variable, so from R to R, we say that the continuity of this function, or this function is continuous at a point x naught, if for all epsilon greater than 0, there exists some delta greater than 0, where epsilon and delta are positive real numbers, such that if x minus x naught is less than delta, so if x is within a distance of delta from x naught, then the function itself, f of x minus f of x naught, is within epsilon, or less than epsilon. So this means that if x is within delta of x naught, then f of x must stay within epsilon of f of x naught for all values of epsilon. Graphically speaking, this is a really nice argument. So suppose you have some function f of x, and you want to kind of parse what this is saying mathematically. This statement is saying that for any epsilon tube that you draw around f of x naught, so this epsilon tube is given by, this is f of x naught plus epsilon, and this value right here is f of x naught minus epsilon. This is saying no matter how small you draw this tube around f of x naught, it can be very, very, very small, this for all epsilon greater than 0, there must exist an interval around x naught. So there must exist an interval around x naught where this interval is the delta interval. This is x naught minus delta. This is x naught plus delta. There must exist this interval such that the function in the epsilon interval stays or the function, sorry, for points in the delta interval, for points right here, right here, right here, will stay always inside the epsilon interval. The idea being that as epsilon gets smaller and smaller and smaller, delta is also getting smaller and smaller and smaller, and the function is approaching, the limit of the function is approaching the value of the function at this point in this small box. And one of the interesting things that we can also note at this point is that this conclusion is actually equivalent to two statements. So this absolute value of f of x minus f of x naught is the same thing as f of x minus f of x naught being greater than negative epsilon and being less than positive epsilon. So if we restrict this definition, say, to one of these other inequalities, specifically we have two inequalities here, so negative epsilon is less than f of x minus f of x naught, or sorry, and f of x minus f of x naught is less than epsilon, we actually obtain the definition. So if we replace the condition that at the full absolute value has to be less than epsilon with one of these two conditions, we actually obtain the definitions of what's called lower semi-continuity and upper semi-continuity. Essentially, this is the definition of continuous from the left or continuous from the right. These are both very, very important concepts that need to be generalized when studying direct methods in the calculus of variations. Now, moving from the definition of continuity for a single variable function, we want to see how this changes for functions of n variables, so multivariable function. So going from a single variable calculus definition of continuity to a multivariable calculus definition of continuity. And realistically, the only thing that's really going to be changing here is the way that we're defining distance in our domain space. Remember, when you go from R, the real numbers, to Rn, you now need to use the n-dimensional norm in this n-dimensional space. And this is really all that changes. So for a function from Rn to R, we see that f is continuous at a point x naught, where this is now a vector because it's a point in n-dimensional space, if for all epsilon greater than 0, there exists a delta greater than 0, such that if the distance between x and x naught is less than delta, this is now a ball or a sphere around the point x naught. If you're using the 2 norm, it's a sphere. If you're using a different norm, it's a different shape. But basically what you're saying is that for every epsilon, there must exist some delta region around the point x naught, such that if you're inside that delta region, so if the distance between x and x naught is less than delta, then for any point in that region, the distance between the value of the function at x and the value of the function at x naught is less than epsilon. Really, it's almost a word-for-word copy of the previous definition of continuity, with the only change being now in n-dimensional space. We're dealing with a vector norm in n-dimensional space instead of just the absolute value function for defining distance. And just like before, we can actually define the lower semi-continuity and upper semi-continuity of our multivariable function in exactly the same way. If we notice that this condition right here, the absolute value of f of x minus absolute value minus f of x naught has to be less than epsilon, actually is two separate conditions. The first being that negative epsilon is less than this difference, the difference of f of x minus f of x naught. If we only take this in our concluding statement here, then we have lower semi-continuity. And if we only take this, which is f of x minus f of x naught is less than epsilon, in this statement right here, then we have upper semi-continuity of our function. Moving on from these two definitions, so the definition in 1D and the definition in ND, I want you to think about how we may extend these two definitions in a very straightforward manner to continuity of a functional. And it's really very straightforward. Specifically, we say that a functional j from some linear vector space of functions is continuous with respect to some norm at the point y naught. Remember, this point is actually a function itself because it's coming from a function space. But it's continuous at the function y naught if for all epsilon greater than 0 there exists a delta greater than 0, such that if the distance between y and y naught in the function space is less than delta, then the distance between the functional value at y and the functional value at y naught is less than epsilon. And it's a very, very incredible thing that this, in fact, is the definition of continuity for a functional, and it comes directly from the concept of continuity in 1D and in ND. The only replacement here now is that the thing that we're talking about the continuity of is the functional itself, and we need to do this operation with respect to distance in our domain space. Our domain space now being a linear function space or a linear vector space of functions that the functional is defined on. And it's worthwhile to sit and think about what this means for a little while, because this is really rather remarkable. We've taken a concept from single variable calculus, which was then extended in multivariable calculus, and we've now taken that and extended it even further to something that is a function from an infinite dimensional space into R. Even for something like this, we can still define continuity. The only difference now is that the distance function is one of those function space norms. It has to be a valid norm on this space of linear functions. And just like before, we can actually extend this to upper and lower semi-continuity as well as before, with some minor modifications when we split this conclusion right here into two separate inequalities. This is an extremely important idea for the direct methods of solving calculus of variation problems. And so what I'd like to do is discuss a few examples that I think are very interesting from a number of different perspectives. Namely, the first one is one that shows up in physics very often. There's this concept of what's called a delta function that's used very frequently by physicists, but this thing is not actually a function at all. It's actually an example of a functional. This is defined in the following way. So if you let J be the functional of the function f, that gives you the value of f at a point x naught in the interval from a to b. So specifically, f here is some function. We're going to take it in the set of continuous functions on the interval from a to b. And here we're taking x naught as a point in this interval. So x naught is some point in the interval from a to b. And this function is just saying when we input the function into our functional, what we get out is the value of the function at a specific point x naught. And we're assuming that the function is a continuous function. So it's in the set of continuous functions. This is called the Dirac delta functional, evaluated at a specific point, or that the Dirac delta functional shifted to the point x naught in the interval from a to b. And historically speaking, the reason why this functional came about and was so important was because physicists needed a way of defining a finite mass to a point for, say, point charges or point masses in theory of gravitation, or for instance, to point charges in electrostatics, in electromagnetics. However, there is no function that has an integral at a point which is non-zero. So the physicist wanted something that would give them something along the following lines: the integral of this delta function times a function f of x on some interval from a to b. They wanted the integral of this delta times f of x to output the value of the function f of x naught for some point on the line from a to b, where delta of x represents a point mass. So it's zero everywhere except for at the point. This is in A to B right here. This is the point x naught. They want it to be zero everywhere except for at x naught. And unfortunately, this is just not possible with the integral. And this is one of the reasons why when you hear someone say Dirac delta function, technically there is no function that satisfies this property. So there's really no such thing as a Dirac delta function. However, it was noticed that if you took the limit of functions with a constant area, so an area of 1, as they tended closer and closer and closer, and the support of these functions got smaller and smaller and smaller, that limit would converge to something reasonable. And this is the starting point of the study into the Dirac delta functional. It turns out that there are a number of ways of defining some sort of mathematical object like this delta. One very nice way of doing this is with the concept of a measure in measure theory. And it turns out that directly connected to that concept of viewing this delta as a measure, or a point measure, is this concept of viewing it as a functional. And these two viewpoints have a very, very nice mathematical connection between the two ways of viewing what this Dirac is. It turns out that you can view it either as a measure or a functional, and these two views are equivalent to one another. So we're just going to go through and use this Dirac delta functional at the point x naught, and we're going to show that it's a continuous functional, because it's a relatively straightforward argument based on the previous definition of continuity. So in order to prove that this is a continuous functional at a point or at a function y naught, we need to go through and fix epsilon greater than 0, and then we need to find some delta such that for any value of epsilon, so with any arbitrary value of this fixed epsilon, we satisfy the condition that if y minus y naught is less than delta, then the absolute value of j of y minus j of y naught is less than epsilon. And this is a relatively straightforward argument, because if we just look at the norm, remember we're going to use are taking our functions in the space of continuous functions. So specifically, we're going to be using the maximum norm talked about previously in the norm lecture. The norm of any function in this space we're choosing in this class to be the maximum value of the absolute value of the function over the entire domain space, so x from a to b. So if we fix epsilon greater than 0, then for any two functions y and y naught in our function space C0, then the norm of y minus y naught is exactly equal to the maximum value over the interval from a to b of the absolute value of y of x minus y naught of x. And this is very, very important, because now we actually, without much effort at all, can find the delta that works for this epsilon. Specifically, if we choose delta equals epsilon, then we're going to be assuming that the maximum value of y minus y naught in absolute value is less than this delta. And now all we need to do is show that when this is true, when y minus y naught is less than delta, then the difference of values of the functional has to be less than epsilon. And so this is clear if you look at the value of the functional, j of y. It's the Dirac delta functional, so this is going to be just the function y evaluated at x naught. And the value j of y naught, evaluated at the function y naught, is the value of y naught, this function, at the point x naught. So the absolute value of j of y minus j of y naught is equal to the absolute value of y of x naught minus y naught at x naught, because that's the value of each one of these individual functionals. And by definition of the maximum, this is going to be less than or equal to the maximum value of the absolute value of y of x minus y naught of x. But this, you'll recall, is the same thing as the norm of y minus y naught. So this entire thing is less than delta. And this ensures for us that this functional is continuous, because it's saying that for any epsilon, if y minus y naught is bounded by delta, then we can choose an epsilon, or we can choose a delta equal to epsilon, such that the functional also stays bounded by this epsilon. Because remember, we've chosen delta to be equal to epsilon here in this proof. So this shows that the Dirac delta functional is a continuous functional. For the next example, let's consider the following. We'll take a function alpha of x that is continuous, so a function that is in C0 on the interval from a to b, and we'll define the functional j in the following way. We'll say that j of f is equal to the integral from a to b of alpha of x times f of x dx. So this functional is defined for f that are continuous, because the product of two continuous functions is continuous. So we're working in the space for f continuous, and we're working with the maximum norm on f. So just like before, the norm of x will be the maximum value over the interval from a to b of the absolute value of the function f. So it turns out that this is a continuous functional, mainly because of that previous definition of continuity. We'll start to prove this by fixing some epsilon greater than 0. And we'll note that the norm of y minus y naught is the maximum value over the interval from a to b of the absolute value of y of x minus y naught of x, just like before. Y and y naught are both continuous functions, so this maximum is well defined, and we'll call it capital M. And finally, we'll recall that the integral of a function, a continuous function, will always be bounded by a specific value from calculus 1. If you do the integral of a continuous function g over the interval from a to b, this will always be bounded in absolute value by the maximum over the interval from a to b, or x from a to b, of the absolute value of the function g times the length of the interval from b to a. And this is a result from calculus 2. However, it's exactly what we need, because what we're looking at is the absolute value of j of y minus j of y naught, which is the same thing as the absolute value of the integral from a to b of alpha times y minus the integral of alpha times y naught, which is alpha of x times y of x minus y naught of x and we know that this integral from this theorem from calculus 1 will always be less than or equal to the maximum value of this entire thing, which is the maximum value of the absolute value of alpha of x times the absolute value of y of x minus y naught of x times b minus a and this entire thing right here can be written as I'll call it m alpha for the maximum value of alpha times our m from before, which is the maximum value of y minus y naught, times b minus a. So if we choose delta to be equal to epsilon over m alpha times b minus a, we achieve the desired inequality. And the reasoning for this is that if delta equals epsilon over m alpha times b minus a, then if the norm of y minus y naught is less than this delta, epsilon over m alpha times b minus a, we know from the calculus 2 theorem that the functional difference, the absolute value of that, will be less than or equal to m alpha times m times b minus a, but m here is less than delta, so this thing is less than m alpha times delta times b minus a, which is in fact equal to epsilon. And for my final example, I'll leave you with the functional that's in some sense a generalization of the previous example. This is the integral from a to b of a function alpha naught of x times a function f of x plus alpha 1 of x times a function f prime of x, the derivative of f, all the way up to the nth derivative of the function f. Where we're assuming that f is in the set dn of ab, which means that f has an nth continuous derivative, which means all of the prior derivatives are also continuous, and we're using that maximum norm for the sum of the function and its derivatives, and the alpha k here are all assumed to be continuous functions as well. I'm not going to prove this because it's very similar to the above, just a little bit more complicated, but this is another continuous functional, and functionals of this form are going to be very, very important for what we're studying a little bit later on in the course as we kind of move on into a more advanced understanding of functionals. And I'd like to end the lecture by defining a very important property that many functionals have, and this property is going to be extremely important for us as we obtain a better understanding of what it means to take the derivative of a functional. And this is the property of linearity, so what it means to be a linear functional. So a functional L from some norm space into R is a linear functional or is said to be a linear functional if the following is true. There's three main axioms. The first axiom is that the functional evaluated at alpha times y must be equal to alpha times the functional at y. These axioms are true for all y in this linear norm space and for all alpha in the underlying field, which we're taking to be R. L of y1 plus y2 for two separate elements in this function space must be equal to L of y1 plus L of y2 for any y1, y2 in S. It's like this holds for all y in S and for all alpha in the field. And finally, 3, L must be a continuous functional for all y in S. And all of the prior examples, the three prior examples that I showed, are in fact continuous linear functionals. So they're both continuous and linear, and you see that continuity is one of the main things that's necessary to be a continuous functional. So it'd be good for you to go through and verify 1 and 2 for each of the prior examples and be able to explain why that holds. But I think that will conclude the lecture for this lecture 2. This gives us all of the necessary preliminary work for really understanding the mathematics of the calculus of variations, and I'm looking forward to the next lecture where we're going to discuss the definition of the variational derivative. Thank you very much for tuning in. I hope you had a fantastic day and that you learned something new.